So last time we read through a little bit of chapter 4, and we tried doing sort of intermittently reading a section and then coding a section. And we got through basically the main loop of the interpreter, or the main, logic where you supply the arguments and it either runs a script or runs a REPL. And then we started down the road of making the scanner and deciding on our representation for the types of tokens that there are. But like what I ended up noticing is we sort of needed knowledge from later on in the chapter to justify lines or translations of lines from earlier in the chapter. So I think this time I will just try reading through. So we know the concepts, and then coming back and implementing the code. And then we won't move on to the next chapter until we have implemented the stuff from this chapter, because I think the chapters are roughly broken down into modular pieces of code. Okay, so yeah, I will go ahead and keep reading from where we were. I think we sort of read up to this error handling section, and then we decided to just go work on more interesting things in the code. But so I'll read this error handling section, and then continue on to more of chapter 4. Okay. While we're setting things up, another key piece of infrastructure is error handling. Textbooks sometimes gloss over this because it's more a practical matter than a formal computer science-y problem. But if you care about making a language that's actually usable, then handling errors gracefully is vital. The tools our language provides for dealing with errors make up a large portion of its user interface. When the user's code is working, they aren't thinking about our language at all. Their headspace is all about their program. It's usually only when things go wrong that they notice our implementation. When that happens, it's up to us to give the user all the information they need to understand what went wrong and guide them gently back to where they're trying to go. Doing that well means thinking about error handling all through the implementation of our interpreter starting now. So they got error, which I guess just means sort of throw an error, add a line with this particular message. This error function and its report helper tells the user some syntax error has occurred on a given line. That is really the bare minimum to be able to claim you even have error reporting. Imagine if you accidentally left a dangling comma in some function call and the interpreter printed out error, unexpected comma somewhere in your code. Good luck finding it. That's not very helpful. We need to at least point them to the right line. Even better would be the beginning and end columns so they know where in the line. Even better than that is to show the user the offending line, like this, point to where the error is. I'd love to implement something like that in this book, but the honest truth is that it's a lot of grungy string manipulation code. Very useful for users, but not super fun to read in a book and not very technically interesting. So we'll stick with just a line number. In your own interpreters, please do as I say and not as I do. Primary reason we're sticking this error reporting function in the main locks class is because of that had error field. It's defined here. We'll use this to ensure we don't try to execute code that has a known error. It lets us exit with a non-zero exit code, like a good command line citizen should. So they have a global bool. Interesting. Okay. We'll have to deal with that. We need to reset this flag in the interactive loop. If the user makes a mistake, it shouldn't kill their entire session. The other reason I pulled the error reporting out here instead of stuffing it into the scanner and other phases where the error might occur is to remind you that it's good engineering practice to separate the code that generates the errors from the code that reports them. Various phases of the front end will detect errors, but it's not really their job to know how to present that to a user. In a full-featured language implementation, you will likely have multiple ways errors get displayed. On standard error, in an IDE's error window, logged to a file, etc. You don't want that code smeared all over your scanner and parser. Ideally, we would have an actual abstraction, some kind of error reporter interface that gets passed to the scanner and parser so that we can swap out different reporting strategies. For our simple interpreter here, I didn't do that, but I did at least move the code for error reporting into a different class. With some rudimentary error handling in place, our application shell is ready. Once we have a scanner class with a scanTokens method, we can start running it. Before we get to that, let's get more precise about what tokens are. Lexemes and tokens. Here's a line of LOX code. var language equals LOX. Here, var is the keyword for declaring a variable. That three-letter sequence var means something. But if we yank three letters out of the middle of language, like GUA, those don't mean anything on their own. That's what lexical analysis is about. Our job is to scan through the list of characters and group them together into the smallest sequences that still represent something. Each of these blobs of characters is called a lexeme. In that example line of code, the lexemes are var language equals LOX semicolon. The lexemes are only the raw substrings of the source code. However, in the process of grouping character sequences into lexemes, we also stumble upon some other useful information. When we take the lexeme and bundle it together with that other data, the result is a token. It includes useful stuff like token type. Keywords are part of the shape of the language's grammar. So the parser often has code like, if the next token is while, then do. That means the parser wants to know not just that it has a lexeme for some identifier, but that it has a reserved word and which keyword it is. The parser could categorize tokens from the raw lexeme by comparing the strings, but that's slow and kind of ugly. Instead, at the point that we recognize a lexeme, we also remember which kind of lexeme it represents. We have a different type for each keyword, operator, bit of punctuation, and literal type. There are lexemes for literal values, numbers and strings, and the like. Since the scanner has to walk each character in the literal to correctly identify it, it can also convert that textual representation of a value to the living runtime object that will be used by the interpreter later. Back when I was preaching the gospel about error handling, we saw that we need to tell users where errors occurred. Tracking that starts here. In our simple interpreter, we note only which line the token appears on, but more sophisticated implementations include the column and length too. We take all of this data and wrap it in a class. Okay, so this class we partially implemented last time, but here he's got token type, the lexeme that makes up the token, the literal value if it applies, and the line where the token was scanned, the original code. And the only method on here is a debug string, printing it up. Now we have an object with enough structure to be useful for all of the later phases of the interpreter. Regular languages and expressions. Now that we know what we're trying to produce, let's, well, produce it. The core of the scanner is a loop. Starting at the first character of the source code, the scanner figures out what lexeme the character belongs to and consumes it and any following characters that are part of that lexeme. When it reaches the end of the lexeme, it emits a token. Then it loops back and does it again, starting from the very next character in the source code. It keeps doing that, eating characters and occasionally excreting tokens until it reaches the end of the input. The part of the loop where we look at a handful of characters to figure out which kind of lexeme it matches may sound familiar. If you know regular expressions, you might consider defining a regex of some kind for each kind of lexeme and using those to match characters. For example, LOX has the same rules as C for identifiers, variable names, and the like. This regex matches 1. So, starts with a letter or an underscore followed by any number of letters, underscores, or digits. If you did think of regular expressions, your intuition is a deep one. The rules that determine how a particular language groups characters into lexemes are called its lexical grammar. In LOCS, as in most programming languages, the rules of that grammar are simple enough for the language to be classified a regular language. That's the same regular as in regular expressions. You very precisely can recognize all of the different lexemes for LOCS using regexes if you want to, and there's a pile of interesting theory underlying why that is and what it means. Tools like Lex or Flex are designed expressly to let you do this. Throw a handful of regexes at them, and they give you a complete scanner back. Since our goal is to understand how a scanner does what it does, we won't be delegating that task. We're about handcrafted goods. So the scanner class. Without further ado, let's make ourselves a scanner. So scanner has a source code and a list of tokens. We store the raw source code as a simple string, and we have a list ready to fill with tokens we're going to generate. The aforementioned loop that does that looks like this. Scan tokens. Yeah, so repeatedly take the next token, and then add an end of file token when you reach the end. The scanner works its way through the source code, adding tokens until it runs out of characters. Then it appends one final end of file token. That isn't strictly needed, but it makes our parser a little cleaner. This loop depends on a couple of fields to keep track of where the scanner is in the source code. Okay. The start and current fields are offsets that index into the string. The start field points to the first character of the lexeme being scanned, and current points at the character currently being considered. The line field tracks what source line current is on so that we can produce tokens that know their location. Then we have one little helper function that tells us if we've consumed all the characters. So isAtEnd returns whether the current character is greater than the length of the source. There's after the end of the source. Recognizing lexemes. In each turn of the loop, we scan a single token. This is the real heart of the scanner. We'll start simple. Imagine if every lexeme were only a single character long. All you would need to do is consume the next character and pick a token type for it. Several lexemes are only a single character in LOCS, so let's start with those. So you need this advanced thing where you move current forward one character and then return the source at that character. So you advance, and then you see if it's one of these, and add the corresponding token if it is. The advance method consumes the next character in the source file and returns it. Where advance is for input, add token is for output. It grabs the text of the current lexeme and creates a new token for it. We'll use the other overload to handle tokens with literal values soon. Before we get too far in, let's take a moment to think about errors at the lexical level. What happens if a user throws a source file containing some characters LOCS doesn't use, like these, at our interpreter? Right now, those characters get silently discarded. They aren't used by the LOCS language, but that doesn't mean the interpreter can pretend they aren't there. Instead, we report an error. So if it's not one of the accepted tokens, you use this error thing, say unexpected character. Note that the erroneous character is still consumed by the earlier call to advance. That's important so that we don't get stuck in an infinite loop. Note that we also keep scanning. There may be other errors later in the program. It gives our users a better experience if we detect as many of those as possible in one go. Otherwise, they see one tiny error and fix it, only to have the next error appear, and so on. Syntax error whack-a-mole is no fun. Don't worry, since had error gets set, we'll never try to execute any of the code, even though we keep going and scan the rest of it. Oh, interesting, okay. Was there already code that used that? I don't think so. Yeah, we're not executing anything yet, so. Okay. No, sorry, lost track. Okay, operators. We have single character lexemes working, but that doesn't cover all of Lex's operators. What about exclamation mark? It's a single character, right? Sometimes, yes, but if the very next character is an equal sign, then we should instead create a not equal lexeme. Note that the bang and equal are not two independent operators. You can't write bang space equal in LOX and have it behave like an inequality operator. That's why we need to scan not equal as a single lexeme. Otherwise, less than, greater than, and equal can all be followed by equal to create the other equality and comparison operators. So here they are. He's modifying I don't know what match means. Okay. Match means look at the current character, and if it's not expected, return false. Otherwise, advance and return true. Interesting. Okay. So it's like a conditional advance. We only consume the current character if it's what we are looking for. Using match, we recognize these lexemes in two stages. When we reach, for example, bang, we jump to its switch case. This means we know the lexeme starts with bang. Then we look at the next character to determine if we're on a not equal or merely a not. Longer lexemes. We're still missing one operator, slash for division. That character needs a little special handling because comments start with a slash too. So if you have a slash and the next character is a slash, then you've started a comment. So you keep consuming characters until you reach a new line or the end of the file. Otherwise, you have encountered a single slash. So it means whatever it means semantically. Okay. This is similar to the other two character operators, except that when we find a second slash, we don't end the token yet. Instead, we keep consuming characters until we reach the end of the line. This is our general strategy for handling longer lexemes. After we detect the beginning of one, we shunt over to some lexeme-specific code that keeps eating characters until it sees the end. We've got another helper, peek. If it's at the end, return a halt character. Otherwise, return the current character. It's sort of like advance, but doesn't consume the character. This is called look ahead. Since it only looks at the current unconsumed character, we have one character of look ahead. The smaller this number is, generally, the faster the scanner runs. The rules of the lexical grammar dictate how much look ahead we need. Fortunately, most languages in wide use peek only one or two characters ahead. So where did you need peek? Okay, conditionally advance through the comment. Because you don't want to start one character into the next line. You want to start at the beginning of the next line. Comments are lexemes, but they aren't meaningful, and the parser doesn't want to deal with them. So when we reach the end of the comment, we don't call add token. When we loop back around to start the next lexeme, start gets reset, and the comments lexeme disappears in a puff of smoke. While we're at it, now's a good time to skip over those other meaningless characters, new lines, and white space. Okay. When encountering white space, we simply go back to the beginning of the scan loop. That starts a new lexeme after the white space character. For new lines, we do the same thing, but we also increment the line counter. This is why we used peek to find the new line ending a comment instead of match. We want that new line to get us here so we can update line. Okay, that makes more sense. Our scanner is getting smarter. It can handle fairly free-form code like this is a comment, groupings, operators. String literals. Now that we're comfortable with longer lexemes, we're ready to tackle literals. We'll do strings first, since they always begin with a specific character, double quote. Okay. So if it's a double quote, you call this string function. And what is string? You peek until you reach another double quote. And then eventually, by this point, you're at the closing quote.
So
Yeah.
does that mean that it reads in new lines in the string?
Yes, I
Okay.
think so. So let's look at this. So it still increments the line counter when it encounters a new line within the string literal, is what it's saying here. So you keep peeking characters until you reach a close quote. And if that character happens to be a new line, then you increment the line counter, just like you would if you encountered a new line here. And regardless of what, as long as you haven't reached the end of the close quote, advance one character further.
Okay.
So by the end here, we've advanced through all the characters until we reach the close quote. So consume that one, and then extract the value from what we just scanned. So it is everything except the surrounding quotes, and then you add a string literal with that value.
And it seems like this language does not have a way of representing an escaped quote mark inside a quoted string.
Yeah, I assume they just did
yeah.
it to keep it simple.
Yeah. Let's see. Does he actually talk about that? Maybe. Like with comments, we consume characters until we hit the close quote that ends the string. We also, yeah, like if you wanted to handle that, it would just be like a special case here for if the character is a backslash, and then you handle the next one in a special way. Okay.
Yeah, if it's a backslash, then the next character has to be one of a small list.
Yeah. We also gracefully handle running out of input before the string is closed and report an error for that. For no particular reason, Block supports multi-line strings. There are pros and cons to that, but prohibiting them was a little more complex than allowing them, so I left them in. That does mean we need to update line when we hit a new line inside a string. Finally, the last interesting bit is that when we create the token, we also produce the actual string value that will be used later by the interpreter. Here, that conversion only requires a substring to strip off the surrounding quotes. If Lock supported escape sequences like \n, we'd unescape those here. Oh, interesting. Okay. Except you do have to not, if you want specifically \double quote, you can't, that has to be a special case, because otherwise you'll hit this. All right. So number literals. All numbers in locks are floating point at runtime, but both integer and decimal literals are supported. A number literal is a series of digits, optionally followed by a dot and one or more trailing digits. We don't allow a leading or trailing decimal point, so these are both invalid. We could easily support the former, but I left it out to keep things simple. The latter gets weird if we ever want to allow methods on numbers, like 123 dot square root. To recognize the beginning of a number lexeme, we look for any digit. It's kind of tedious to add cases for every decimal digit, so we'll stuff it in the default case instead. Okay. That seems like a limitation of Java switch statements, but that's fine. So if it's a digit, we scan a number. Otherwise, return the same error that we were before. Okay. Once we know we are in a number, we branch to a separate method to consume the rest of the literal, like we do with strings. We consume as many digits as we find for the integer part of the literal. Then we look for a fractional part, which is a decimal point, followed by at least one digit. Peek next, so we need 2 characters of look ahead. If we do have a fractional part, again, we consume as many digits as we can find. Looking past the decimal point requires a second character of look ahead, since we don't want to consume the dot until we are sure there is a digit after it. So we add peek next, which is Yeah, just peek two characters ahead. Finally, we convert the lexeme to its numeric value. Our interpreter uses Java's double type to represent numbers, so we produce a value of that type. We're using Java's own parsing method to convert the lexeme to a real Java double. We could implement that ourselves, but honestly, unless you're trying to cram for an upcoming programming interview, it's not worth your time. The remaining literals are booleans and nil, but we handle those as keywords, which gets us to reserved words and identifiers. Our scanner is almost done. The only remaining pieces of the lexical grammar to implement are identifiers and their close cousins, reserved words. You might think we could match keywords like or in the same way we handle multiple character operators like greater than or less than or equal to. So like case O, and then look at the next one. Consider what would happen if a user named a variable orchid. The scanner would see the first two letters, OR, and immediately emit an OR keyword token. This gets us to an important principle called maximal munch, my favorite compiler terminology. When two lexical grammar rules can both match a chunk of code that the scanner is looking at, whichever one matches the most characters wins. That rule states that if we can match orchid as an identifier and or as a keyword, then the former wins. This is also why we tacitly assumed previously that less than or equal should be scanned as a single less than or equal token and not less than followed by equals. Maximal munch means we can't easily detect a reserved word until we've reached the end of what might instead be an identifier. After all, a reserved word is an identifier. It's just one that has been claimed by the language for its own use. That's where the term reserved word comes from. So we begin by assuming any lexeme starting with a letter or underscore is an identifier. Okay. So if it's alphanumeric, scan for identifier. The rest of the code lives over here. So just keep consuming things until you see something that's not alphanumeric. And then add a token for identifier. Wait. Are you recording what the, okay, we'll get there. Are you recording what the name was that you just looked at?
Yeah, exactly.
I assume we'll get there. Okay. We define that in terms of these helpers. So is alpha means are you a through Z or underscore? Is alphanumeric means are you alpha or a digit? That gets identifiers working. To handle keywords, we'll see if the identifier's lexeme is one of the reserved words. If so, we use a token type specific to that keyword. We define the set of reserved words in a map. Okay, so you have a map from the string you match to the token that it actually represents for keywords. Then after we scan an identifier, we check to see if it matches anything in the map. Okay, so this is the missing code. So start is the start of the lexeme. Current is where you ended up at the end of the lexeme. So you get the substring there. You look in the map to see if it matches one of the keywords. If it doesn't match, then it's an identifier. Otherwise, add a token of the type of that keyword.
Don't you have to lowercase it somewhere in there?
Why?
Oh, no, I'm sorry. The keywords are only valid if they're all lowercase. Okay.
Yes. But
So
also,
that
I would think the identifiers that aren't keywords would be case sensitive, so you wouldn't.
right, but that also implies that capital PRINT is just a plain variable, not the word print. Like anything that is not all lowercase is just an ordinary variable, including one that's spelled similar to the keyword.
Right. So yeah, so it would be an exact match in keywords then. So yeah. All right. If so, we use that keywords token type. Otherwise, it's a regular user-defined identifier. And with that, we now have a complete scanner for the entire LOCKSS lexical grammar. Fire up the REPL and type in some valid and invalid code. Does it produce the tokens you expect? Try to come up with some interesting edge cases. See if it handles them as it should. Okay. Let's see about, I actually thought this was interesting. I'll read this. So implicit semicolons. Programmers today are spoiled for choice in languages and have gotten picky about syntax. They want their language to look clean and modern. One bit of syntactic lichen that almost every new language scrapes off, and some ancient ones like BASIC never had, is semicolon as an explicit statement terminator. Instead, they treat a new line as a statement terminator where it makes sense to do so. The where it makes sense part is the challenging bit. While most statements are on their own line, sometimes you need to spread a single statement across a couple of lines. Those intermingled new lines should not be treated as terminators. Most of the obvious cases where the new line should be ignored are easy to detect, but there are a handful of nasty ones. A return value on the next line is value the value being returned, or do we have a return statement with no value followed by an expression statement containing a string literal? A parenthesized expression on the next line. Is this a call to func parenthesized, or two expression statements, one for func and one for a parenthesized expression? A minus on the next line. Is this first minus second, or two expression statements, one for first and one to negate second? In all of these, either treating the new line as a separator or not would both produce valid code, but possibly not the code the user wants. Across languages, there is an unsettling variety of rules used to decide which new lines are separators. Here are a couple. Lua completely ignores new lines, but carefully controls its grammar such that no separator between statements is needed at all in most cases. This is perfectly legit. A equals 1 space B equals 2. Lua avoids the return problem by requiring a return statement to be the very last statement in a block. If there is a value after return before the keyword end, it must be for the return. For the other two cases, they allow an explicit semicolon and expect users to use that. In practice, that almost never happens because there's no point in a parenthesized or unary negation expression statement. In other words, these are dumb edge cases. Go handles new lines in the scanner. If a new line appears following one of a handful of token types that are known to potentially end a statement, the new line is treated like a semicolon. Otherwise, it is ignored. The Go team provides a canonical code formatter, Go format, and the ecosystem is fervent about its use, which ensures that idiomatic styled code works well with this simple rule. Python treats all new lines as significant unless an explicit backslash is used at the end of a line to continue it to the next line. However, new lines anywhere inside a pair of brackets are ignored. Idiomatic style strongly prefers the latter. This rule works well for Python because it is a highly statement-oriented language. In particular, Python's grammar ensures a statement never appears inside an expression. C does the same, but many other languages which have a lambda or function literal syntax do not. An example in JavaScript. Function is an expression, statement is a statement. Yeah, or console.log expression. Python would need a different set of rules for implicitly joining lines if you could get back into a statement where new lines should become meaningful while still nested inside brackets. JavaScript's automatic semicolon insertion rule is the real odd one. Where other languages assume most new lines are meaningful and only a few should be ignored in multi-line statements, JS assumes the opposite. It treats all of your new lines as meaningless white space unless it encounters a parse error. If it does, it goes back and tries turning the previous new line into a semicolon to get something grammatically valid. This design note would turn into a design diatribe if I went into complete detail about how that even works, much less all the various ways that JavaScript's solution is a bad idea. It's a mess. JavaScript is the only language I know where many style guides demand explicit semicolons after every statement, even though the language theoretically lets you elide them. If you're designing a new language, you almost surely should avoid an explicit statement terminator. Programmers are creatures of fashion, like other humans, and semicolons are as passé as all caps keywords. Just make sure you pick a set of rules that make sense for your language's particular grammar and idioms, and don't do what JavaScript did. So I will say we use JavaScript at work without and our like formatting what do you call it? Our config for our formatter says don't put semicolons anywhere, and it's fine. Like if unless you write, like we don't encounter problems with that. It's just like if you write code that is indented normally, it works. Yeah. I'm sure if I looked at the implementation of it, I would get the heebie-jeebies. Okay, so I've now read chapter 4. Let's go back and do the scanning logic that we didn't do last time. So, oh yeah, I never started the live session. I'll go ahead and do that now. So I'm reading the chat. So Nish, what did you mean by note that this doesn't handle escapes?
Well, that was when we were talking about strings.
Oh, okay, like escapes characters. Gotcha. Okay. Yeah. Okay. Where were we at? So we have token type. We have token, which includes that and a lexeme and a line. We decided to implement lexeme as a string reference or an answer into the source. And Michael pointed out we don't need to separately include the literal value here. It can just be a member of the enum for the cases that need it. So if it's one of these, it will have the relevant literal value. Okay. So let's do this loop here. Also, I guess we decided to implement scanner as an iterator over the tokens. So we will get the source, and then scanner will just be, we'll be able to just say like for token in tokens. Like, let's see. So anywhere we can actually do that. Like, did we have run anywhere? Yeah. Well, we'll say for token in scanner, and that'll just reduce all the tokens out here. So let's go ahead and write this next function. So the first thing he did was he had all these helpers. We're gonna, I guess, need these helpers. Let's see. I kind of feel like doing a very
A
literal.
lot of those, you
Yeah,
can
go ahead.
use a lot of the helpers from the string str data type.
I agree. Yeah.
So strip prefix, for example.
So let's see. So advance does move forward and then take the next character. So can I get an iterator over the characters and then like do a take?
I think there is. Are we going to support non-UTF anything other than ASCII characters? If we don't, it would make parsing a bit easier.
Yeah, let's do what he does for now. I think that'd be cool. But doesn't it just change like which iterator you need to use? Like whether you're iterating over characters or bytes or code or whatever you called? Runes? What are they called?
Code
Um,
points.
Yeah, code points.
Well, it makes splitting easier. Okay, with UTF there is split boundary.
Okay.
Okay, so that would be self source self dot source
Yes.
dot
Dot.
chars dot next
So
question mark.
that has to this has to be persistent between the iterations.
No.
So wait,
So
This way you get the first character, but you don't save it anywhere. We will save it later when we decide to return.
yeah, so like I guess if you're trying to port over the way it's written in the book, the issue here is the chars basically will hold onto the iterator, where what you want is kind of an index of what character it is that you're looking at.
yes, that's true. So right. Because his C he has these index variables, the current one and the start of the last lexeme we're looking at.
Yeah.
So
So you could treat your string as a slice and then hold your kind of
yeah,
pointer index somewhere.
yeah. Should I put that just in the scanner, you think?
I think that's
yeah.
fine. It's just going to like then you'd always need a mutable. Oh, okay, I guess you do have a mutable reference to self, so
Yeah,
it
I
should be
do.
okay.
Yeah, it's mutable because we're going to the next
Mhm.
token. I'll stay. I'll use the same names he does. So
Oh, I was looking up and they say there's a peekable function for the iterator or for chars. I don't know if anybody's actually used that or not.
It's not only for cars, it's for any iterator.
Mhm.
so I guess the thing is okay.
And no, we don't want to use that. It's going to be quadratic complexity or something.
I agree.
Yeah, I think it's
So
source.
so yeah, we just need to like index into the source. Yeah.
Exactly.
So and that means what are we sacrificing there? We're assuming that the characters are fixed width.
Yes.
No,
Oh.
we don't have to. Once we get C, we can calculate its width using char.utf-len and advance by that.
Right, but
Okay.
didn't he have a place where when you start a quoted string, then he looks all the way down and finds the end of the quoted string and then just takes the.
We can do the same. We will use find to find the matching clause and quote. It will give us position in bytes, yes. And we can just add that.
Do I want to keep instead of doing this indexing, should I keep an iterator into the source
No,
around? No?
no.
Because we're kind of like, well, what I was thinking is, we're building this iterator over the tokens out of an iterator over the characters, right?
I mean, in this case, no, right? Because you're just accessing it directly. So unless
I will
you
do something
add a second
like
iterator
this.
inside.
a second iterator inside the OR.
Right.
Yeah, that seems right to me.
Something like this.
Okay, so this is get a slice to everything after the current index. Take one
Well,
character.
everything that we need to parse. And next line we get the first character.
Okay. What does he
And
keep? Wait, where does he keep the state of everything? Oh, he doesn't keep the state of everything between start and current. He only like reads that when he needs it, like as a substring. Like yeah, like this. Okay. So sure. So let's do these basic cases. And of course it's not, this is not syntax. I think, what is it, that? And then sorry. And then we don't know what add token is.
that would be a return some token.
Yes, okay.
But at the same time, we need to advance the iterator. So I would save it into variable, then check if it's some, then produce it. And
Wait, say that again?
okay, so all of them will have the same content. So same, the only different part is going to be the token field.
Yes.
So you can assign just
Right.
the token to some variable, like the let e equals, and that is just a token.
But is that pattern going to hold for all the other stuff? Because we have those other functions we're going to need to call for like string.
We can
literals.
factor it out later.
Okay. So if let some,
So first,
Wait.
so that, oops, that would be none.
Yeah.
And that would be, well, how do we call it? Token type?
Yeah, I think that's what you guys called it, yeah.
Type, star,
okay. Yeah, good.
and the rest for everything else. Okay.
So that will give us a token type.
Yeah, in the variable t.
So
So-
why do you need what's if let some doing here? Isn't it just like,
We check, and if we have something, then we adjust
Oh.
current self current then get 8 some and token,
Yeah.
whatever you need.
Um,
Token is already as token variable. Lexem, we need to take a slice from unparsed one character long line we have in self.
Yeah.
so his thing is, okay. Oh, I see, I understand. Okay, Lexeme is not the start, it is the substring from start to current.
No, Lexeme is a substring from unparsed, and the size of that substring is c dot UTF-8 length. Because what we just got was at the beginning of unparsed.
So, okay, isn't it true that, okay, so you're saying unparsed is always from the current
unparsed,
token onward.
yes.
So I guess my question is, for his start field, does that ever reach back into the previous parsed characters?
I am not sure what this.
I'm pretty sure it doesn't. I'm pretty sure that after his code, any time after his code emits a token, it never goes, start never goes backwards ever again.
No, start never goes backwards, but does it at the start of his loop where he's taking the next token? Can start refer to something that he previously scanned? Or is it like one of the, I'll try to explain what I mean. So walnut, okay, walnut is at end, start equals current, and then take one. Yeah, okay, so so by the time we get into here, start is equal to current.
How he uses start.
I think that's right. So start is, if you need to know how, if a multi-character Lexeme was just scanned, start doesn't change while you're iterating over characters, but current does. So that's how you know how long the string literal was and stuff.
That's basically what we have in unparsed.
Yeah, right. So unparsed at 0 is the same as the whole source at start, I think.
Okay. Do we still need start?
Well, it's maybe useful for something like reporting that index somewhere, having the actual index
Okay.
value, but I don't think so, because all of his, whenever he takes a substring, it's always source, yeah, it's source dot substring, something related to start, and then something related to current. So we can just have it be something related to 0 instead of start. So yeah, we don't need start. We can just,
So typically, if you were essentially creating spans to avoid copying the string pretty much everywhere, so you don't have to hold kind of references to it. So that's why you would kind of keep those, but it's your call.
so, don't we already have like, yeah, I think we have everything we need just from this.
Yeah, you have the token, but like not where it was back in the doc. But I guess like he isn't actually making, I guess the author isn't making spans, so maybe it doesn't matter here. I don't know.
So, oh, well, I guess we need, so current is an index into source, not into unparsed. So in order to
We can
have
use
both,
start.
what?
We can use start in unparsed instead of source, instead of current.
And then, but then current needs to be So we need to keep track of our global position within the source. And we also need to keep track of where we are in the current, taking the current token.
Do we need to keep current across different tokens? If not, it can be a local variable inside next.
Yes, I agree. So let's say, so let's make it mean something unambiguous. So maybe it's like we have one number which is just next unparsed character or something.
Or current token length.
It's not the length, it's offset.
Okay.
So if we have that, then it's just you take the next unparsed and so on.
Yep.
And then we'll do some stuff and then let mute length equals 0. We'll do some stuff that will mutate length. And then at the end, it'll be like self dot next unparsed plus equals length. Right?
Yeah, I'm doing it at line 81.
Okay, gotcha. So, but right, and this is it's not. I guess we were sort of this or like implicitly you were doing the entire token, not just the one character.
Yes, well, token for those however many types.
So this should be this.
Next unparsed. Because we return at the next line. There is nothing else to do for this token here.
So, okay, wait. I guess the thing is, okay, we still haven't figured out, we have to do some loop in here to take a multiple.
For those simple tokens now, for those simple tokens we're done.
Yeah. Right.
After that, we check if C is one of those fancier exams. We can try to parse them and handle them. Then the keywords, then the idents.
Okay. Well, okay. So I guess the thing is this won't be common to everything, will it?
It will.
It will? Oh, okay, right, but only because of your thing where you included that in the token type. So everything, all the parsing we need to do is all contained in token type. And then the other fields in token follow the same format all the time.
Something like that.
Okay, cool. Let's try it. So is this right? So we get the token after all the parsing. It can't be C.
It is C because that's the character we just parsed. So,
but if it's more than just, if we end up parsing more than just C because it's like one of the string literals.
So everything between those two lines is we parse in those single character tokens. The longer tokens will parse below, and it will be again match case.
Okay, I see.
And they will be one more if let block. Once we have several blocks, we'll look into how optimize it to reduce the duplication.
Gotcha. Okay. Interesting. So he does it by iteratively modifying this match, but we're just doing more.
Okay.
But yeah, so that's the thing. It's maximal munch, right? So the tokens where okay, I guess we can still do that. So but let's say that this was none. Then we keep going. And then over here we're at the next character.
If you want to keep everything inside single match, we'll have to produce something else.
I'm trying to think if this multiple match thing will work for those. Because we called next.
It will work, but it will be more verbose.
Well, okay. What I'm saying is if we have if it's this,
Okay.
then we have to handle this thing where it's either not equal or not. So we can't consume this character and forget about it.
Right.
So if we do, I guess we won't, if we do another call to this, it'll just take the same one again.
Yeah, we'll have to
Okay.
advance.
So so we do another match on the same character.
Yep.
And if it's one of these,
So one other option is to do something like this. So,
yeah.
is it? And so on. That's
Sure.
one more option.
I like that. Because then it's just in here instead of in a weird match block. Yeah. But then it's oh, can we still use this as an expression? Like,
No. Well, yes, we can. Yes.
yeah, to get the token type out of it. Okay.
And we can advance anything we want inside of it.
Okay. I like that. Cool. All right. Looks like Niche had to drop.
Yep.
I guess I'll stop the recording. Feels like we're getting somewhere. You guys want to wrap it up, or do you want to keep going while we have momentum?
I'll probably have to drop off here, but
Okay.
I can, yeah, just check the GitHub or whatnot.
All right, cool. I'll wrap it up.